Hello, everyone, and welcome to this explainer. I am absolutely thrilled to have you here today. If you've ever stared at advanced physics equations and just felt totally overwhelmed by all the strange angles, shifting coordinates, and rotating dimensions, well, trust me, you are definitely not alone. Today, we're treating this as a beginner-friendly mini course. I promise we're going to break down these complex 2D and 3D coordinate systems into a really logical, easy-to-follow building block tutorial. By the end of our time together, you're going to see the beautiful geometric logic behind exactly how things move. Here's a quick look at our roadmap for today. First, the basics of motion. Second, the static Cartesian grid. Third, tackling rotating frames. Fourth, expanding into 3 dimensions. Fifth, the evolution of energy. And finally, number 6, a quick review for students.
Section 1. The basics of motion. Let's lay down some ground rules before we get into the heavy math.
All right, let's dive right into this. Our overarching goal in this explainer is to really understand the architecture of kinetic energy. To do that, we have to mathematically describe exactly where an object is and how fast it's moving. But to describe movement, we need a common language of dimensions. In classical mechanics, everything essentially boils down to 2 distinct flavors of movement. Our first flavor is the radial dimension. This is simply linear motion. Imagine pushing a block straight across the table, or a rocket shooting directly up into the sky. It is straight-line movement represented by a standard linear distance, so it's measured in meters or feet. This is by far the simplest type of motion to wrap your head around, and it really forms the total foundation of all basic physics problems. Our second flavor is the angular dimension. This is rotational movement. Instead of moving in a straight line, the object is rotating around a central point, or an axis. Think of a merry-go-round, or a planet orbiting the sun. This gives us our second critical tool. Every complex coordinate system we build today will simply be a clever combination of these linear, straight-line dimensions and these angular, rotating dimensions. Section 2. The static Cartesian grid. Let's start with a framework you probably already know. In standard Cartesian space, the unit vectors are wonderfully simple, typically called I, J, and K, representing the X, Y, and Z axes. They are perfectly static. They point in one direction forever. No matter where your particle moves in this space, up is always the exact same up and right is always the exact same right. Because the frame itself isn't twisting or turning, that baseline absolutely never changes. And because those unit vectors are completely frozen in place, the math is incredibly straightforward. Velocity and acceleration just become simple time derivatives of position. If you want the kinetic energy, you just square the linear speeds of x, y, and z, add them up, and multiply by half the mass. It's safe, it's easy, and it works perfectly. Until, that is, your real-world problem involves something spinning. Cartesian creates rigid boundaries that make calculating circular forces a total nightmare. Which brings us to Section 3, tackling rotating frames. Here's where the plot thickens. We really need to clearly contrast our previous model with our new one. In a static Cartesian frame, the grid is basically a rigid cage. But in a dynamic frame, like a 2D plane polar system, the grid moves with the object. Instead of an x and y axis, you track a particle by its distance from the center, that's our radial dimension, and its angle around the center, that's our angular dimension. The fundamental unit vectors that point toward the particle literally pivot and turn as the particle orbits. And this brilliantly illustrates the mathematical consequence of that twist. Because the polar unit vectors pivot to follow the particle, their own time derivatives are no longer zero. The coordinate system itself is moving. It's like you aren't just calculating how fast a car is driving, you're calculating how fast a car is driving while the road underneath it is spinning like a giant turntable. Because the frame is moving, calculating acceleration suddenly explodes into this incredibly intimidating equation. I know, it looks like a massive jumble of Greek letters and dots, but seriously, don't panic. As promised, we're going to break this down into its basic ingredients. This entire equation is simply telling you what happens to an object when it tries to move in a straight line while its environment is actively twisting around it. Think of these extra pieces of math as necessary scaling factors. On the radial side, you get a centripetal factor. This is that familiar force you feel pulling you outward on a spinning carnival ride. On the transverse, or angular side, you get the Coriolis factor, which is that strange curving effect you see when you try to roll a ball straight across a spinning merry-go-round. They aren't just random variables, they are the absolutely natural ingredients required to correct the math when you introduce rotation.
Section 4, expanding into 3 dimensions. Time to upgrade our 2D plane into full 3D space.
Mathematicians realized there are two distinct, highly logical strategies to add a third dimension to a flat spinning circle. Strategy A is to take that spinning 2D circle and simply stack it vertically, layer upon layer. This gives us cylindrical coordinates. Strategy B is to take that 2D circle and pivot the entire plane vertically around the center point. This gives us spherical coordinates. Let's see how these look. Visualizing these two strategies makes it so much clearer. Strategy A keeps the horizontal plane exactly the same, but we add a straight up and down z-axis. That perfectly outlines a cylinder. Strategy B, on the other hand, takes the flat plane and sweeps it up and over like a dome, relying entirely on angles to map the height. And that, naturally, outlines a sphere. Let's see how this builds into the math. With the cylindrical model, notice how the kinetic energy equation just tacks on a standard, boring Cartesian z-squared derivative at the end. The vertical axis is totally static. But the spherical equation, that is wildly different. It relies on a really complex mix of two angles, theta and phi, alongside the linear distance r to calculate that kinetic energy. To truly master the spherical system, you have to understand this specific spatial logic. Theta is an angle measuring the vertical drop from the top pole. It is a declination angle. It is crucially not a rotation about an axis. Phi, meanwhile, is the equator-like band that actually represents horizontal rotation around the z-axis. Mixing these two up is literally the #1 mistake students make, so definitely keep that straight. Section 5, the evolution of energy. This is the climax where all our math converges. Here you can visually see the scaffolding of physics. At the base level, with 0 rotations, we have our pure Cartesian math. Add one 2D spin, and we get plane polar. Stack a height vector on that, and we get cylindrical. Finally, add a second full 3D spin, and we get the formidable spherical kinetic energy equation. Every single layer logically builds on the one right before it. It's like a giant, beautiful puzzle. Section 6, quick review for students. Let's lock in everything we've just learned. Consider this your ultimate system selection matrix, basically a cheat sheet for picking the right mathematical tool. If your problem is a box sliding down a straight ramp, you use Cartesian. All linear variables, super simple. If your problem has axial symmetry, like a bead sliding up a twisting wire, you use cylindrical. It mixes linear height with a 2D spin. But if your problem features point symmetry, like forces radiating from a center, such as a planet's gravity, you absolutely must embrace the complex trigonometry of spherical coordinates. So the crucial takeaway is this architectural rule right here. Whenever you're translating pure rotation into a physical velocity to calculate kinetic energy, a naked angle is meaningless. You can't just square an angular velocity. An angular dimension always requires a radial scaling factor squared attached to it. A tiny gear spinning at 10 RPMs has very little physical velocity at its edge, but a giant windmill spinning at 10 RPMs, that has a massive physical velocity at its edge. The radius scales the rotation. Now I want to leave you with a real-world challenge. Imagine a satellite orbiting a rotating Earth. Based on what we just learned about base geometries and matching your tools to your problem, which of these 3 frameworks, Cartesian, cylindrical, or spherical, would you choose to elegantly calculate its path? Think about that central point of gravity. Think about the angles. Thank you so much for joining me on this explainer. Keep asking great questions, and I'll see you next time.